Good evening, everyone. Sorry about the late start tonight. I lost track of time and decided I should eat before I streamed, so apologies for that. How's everyone's weekend going? Mongo, good to see you again, hanging around in the chat. Welcome. It was really good to have you on Mongo last time, schooling me on IDA and picking up on my mistakes, so very much appreciated your input. Wanted to kick off tonight with a couple, in case you missed it, deals that are going on right now. Just going to copy some bookmarks from my browser. First of all, YubiKeys. If you don't use a YubiKey, you should pick up a YubiKey. They are on sale right now. I think for the next couple hours, you can do a buy one get one free on the YubiKey 4, and then tomorrow, I think this one kicks off, which is you buy one get one free on eligible YubiKeys. So if you don't want the YubiKey 4, if you want the YubiKey Neo, which has NFC support, or if you want the cheaper, I think it's called the U2F option. Yeah, FIDO U2F for just non-OTP, non-RSA, single sign-on, or not single sign-on, 2FA for GitHub and stuff. You can pick up a cheaper blue YubiKey. I love my YubiKey. I don't use it for OTP, the one-time password function, as much as I use it to keep my keys. I've found the YubiKey really, really good for holding on to RSA keys. So, for example, my PGP keys, I actually really want to do a stream one day on how I do PGP. But I've got a master PGP key, which sits offline, sits on an SD card hidden somewhere. And what that key can do is it can create new subkeys and kind of join them into my little collection of keys. And that key never gets used except to generate new subkeys. And then the subkeys, which actually do my, first of all, encryption or decryption when people encrypt stuff to me, sits on my YubiKey, and it sits offline in case I lose my YubiKey. My subkey that does signing for signing Git commits and signing emails and stuff sits on my YubiKey. The third subkey on my YubiKey is an authentication subkey, which is actually an SSH key. So if you were to look in my /.ssh, there is no SSH private key there. There's a public key but no private key. If you look in my /.gnu-pg, there are no private keys there. So if someone was to pinch my laptop, they don't actually get a copy of my keys. You would need to steal my YubiKey, and the YubiKey you can then put a PIN number on it. So each time you plug it and unplug it and plug it and unplug it, it will challenge you for the passphrase again. And if you get the passphrase wrong a user configurable number of times, then the YubiKey will brick itself. I don't know if it's a soft brick or a hard brick, but it will keep your keys safe so someone can't brute force the PIN number. So the theory is, what you can do at Wolf, yeah, no worries, I'll make sure I hook that up. I've really wanted to do it for a long time, so I will make sure it happens. So the net effect is, for the buy one get one free, you can do two of them for 45, or I think $40 US, with free shipping. And then if you wanted to get the Neo, like the Neo does support NFC, so you can actually use it with your mobile phone in some wacky fashion. What I really am excited about, because I've already got the Neo, what I'm excited about for the YubiKey 4, as opposed to the Neo, is the Neo supports 2K RSA keys. The YubiKey 4 supports 4K RSA keys. So you can have stronger PGP subkeys and a stronger SSH key with the YubiKey 4, with the YubiKey Neo. I mean, 2K, 2048-bit RSA keys are still pretty good, but I'm excited about, I've got my PGP subkeys coming up for expiration early next year, so I'm going to use that as an opportunity to have 4K PGP keys from now on. My master key has always been 4K, so it's going to be 4K the whole way through. So yeah, the net effect is if you've got a YubiKey and you put your PGP keys and your SSH keys on it, you actually need to plug it into your computer, and then your computer can use those keys without knowing those keys. So if your computer gets compromised or stolen, it's difficult for an attacker to actually get a reusable instance of your key. If your machine gets compromised and your YubiKey is plugged in, then the attacker can use your keys, but they can't extract your keys to use them at a later date. So YubiKey is a super cheap, super convenient, like you don't actually need a smart card reader in your machine, you just need a USB. socket, and you've got basically a hardware security module, basically a smart card that can hold your keys and expose them for use, but not expose them for export. So I think that is really cool. If you're on the fence about getting a YubiKey, just do it. They're a lot of fun, at the very least, just to play with. The second, where's the bookmark? The second, in case you missed it, deal going on right now is the Humble Bundle of Unix books. I can't really kind of vouch for any of these. The Sed and Awk one I have flicked through. It is a brilliant reference if you're writing Awk scripts. Of course, I mean, the Bash book, the Bash, the shell scripting, the Bash cookbook, they're going to be useful. If you use Emacs, then I'm sure the Emacs book would be useful. The Vim book, I'm sure is going to be good when I get to it. I've heard a lot of really good things about Unix power tools. I've had a quick flick through it. It didn't seem like it had anything terribly earth-shatteringly new to me, but if you're new to Unix, then you'll probably pick up a lot of really cool stuff out of the Unix Power Tools book. And then if you pay $1 or more, you get these books. Pay $8 and you get all of these books here, including the top row and the middle row. $15 gets you the whole lot. The DNS and Bind book is quite good. I haven't read the other 3 in this tier. But if you're looking to expand your professional ebook library, then there's a bunch of Unix books on sale for the next week and a half. Yep, week and a half. So consider the Humble. And the good thing about Humble book bundles is that you can select at checkout which charity it will support. So you can go pay $15 to get the whole lot, choose where your money goes, and you can choose to give money to the publisher. You can choose to give money to, I think the EFF is in here if you support the EFF. The Wikimedia Foundation's in there. EFF? Electronic search. Yeah, there you go. The EFF is in there as well. So you can actually, if you really wanted to, give the publisher no money, give Humble no money, and give all of your $15 to a charity of your choosing. So it's a really good way to pick up some books and add them to the library and support charity. So those are my 2, in case you missed it, deals going on right now, and I encourage you to check them out. Of course, I'm not at all supported by YubiKey or Humble Bundle. YubiKey and Humble Bundle, if you want to support me, get in touch. I just think these are really good deals. I have actually picked them both up. The YubiKey 4 I've been looking forward to for the 4K keys, and I'm a sucker for book bundles, so I've picked them both up, and you should check them out. Rightio, in terms of tonight's stream, I thought we would check out a binary that really tickled me early this year. Much like bin2json from the other night, this surprised me, this pleased me because it wasn't a stack buffer overflow. We're going to come back to stack buffer overflows. I don't know, if people want to see more stack buffer overflows, we'll go back to them and we'll do them until we're all sick of them, and we'll do them until we're all totally on top of them. But this is a really novel binary. It's called Butterfly. There's a bunch of write-ups, so if you don't like the way I solved it and you want to read someone else's write-up, you can do that. Otherwise, there's a link in the channel description to this page here. You click on this and you get a download of the binary. There it is, the download button. As well as a README, which tells you the challenge briefing, which doesn't really tell us too much. We know it's called Butterfly. Some nonsense about the universe smiling on you, and then other times you've got to do the hard work. Of course, this challenge server's probably not up anymore. I doubt they would have left it up all year. Oop, nope, don't need -n. Yeah, it looks like that challenge server is dead. But we can shell it locally, and they tell you that during the challenge they updated the binary, please re-download it, and a bunch of write-ups. So let's get into it. We've also got the same issue we had last night, or the other night, with VirtualBox. My VirtualBox is still totally screwy, so unfortunately we cannot resize the VirtualBox window, or else we can't use VirtualBox for the rest of the night. Because i3 and VirtualBox are not playing nicely together at the moment. So if we want to use IDA, we've got to use it full screen, and we can't resize it, unfortunately. So good to have everyone around. I've got Unix in a nutshell Oh, interesting. Because I mean, I was thinking Unix books are going to age pretty damn well. You can't really go wrong buying Unix books because Unix doesn't change. But apparently, Unix in a nutshell was full of vendor-specific commands. There's still a lot that works on modern distros. So you can get 4 books, for instance, for £12. Well, £12. I'm not sure how much £12 is worth in funny money. But the idea with the book bundles is you can pay $1 and you get these 1, 2, 3, 4, 5 books. You can pay $8 or more to also get this tier here, and you get 1, 2, 3, 4, 5 books plus this tier. Or you can pay $15 to also unlock these. So if you pay $15 US, you get these 4, you get this tier, and you get that tier. So they accumulate the more you pay. And of course, you're more than welcome to pay more than $15 if you want to support charity to any extent you wish. So that's how those tiers of books work. Is the cheap Shodan access still active? I'm not sure. I've actually got a Shodan account from many years ago. I don't use Shodan much anymore. Was it on their homepage? Are they Shodan.io these days? Shodan Black Friday? Because yeah, good call. If the $5 deal is still on for Shodan, if you don't have a paid Shodan account, you should probably chuck $5 in the hat and pick up a lifetime membership. But I'm not sure. Doesn't maybe you have to log in to actually get the deal. If you don't have Shodan, yeah, check that out. Good call. At Wolf. Yeah, so it's like, yeah, you pay the top tier, you get all the books in all 3 tiers. Hey, CPM Gaming Ltd, no, we cannot hack this person. He keeps messing your dedicated server up. This is not the place to ask for hackers for hire. I can only speak for myself. Someone in the room might help you out, but I don't approve of that. I'm a professional. I work in IT, in information security. So, no, I'm not going to do hacking of stuff for you. And if there's any more questions along those lines, there will be timeouts handed out because we don't tolerate that here. Let's get into Butterfly, hey? Twitch Butterfly. Alrighty, so, oops, no, we want to do this. So what do we get? We get a file named Butterfly. It's a 64-bit ELF executable, dynamically linked, blah blah blah. It's not stripped. Cool. Let's chuck it into IDA and see what it looks like. In fact, here's one I prepared earlier. Butterfly. So we'll pull this one up. So I have solved this before. I solved it basically during this CTF, so it looks like it hit the repo about 5 months ago. It's probably about 5 months ago that I solved this. I can remember what the bug is. I can remember vaguely how I did the exploit, but the exploit is a lot of fun to write, and it's been a couple of months since I've written this exploit, so I'll be doing it from scratch tonight. As for where the bug is, this binary is unashamedly a bug as a service, so reverse engineering and trying to decide where the bug is not at all the point of this challenge. The point of this challenge is this service is basically a bug class as a service. What are you going to do with it? It's a lot of fun. So we'll pull Butterfly into IDA, and we get a main function. The main function is going to call setBuff, just to unbuffer stood out so that it prints stuff as soon as you connect. Calls puts, it calls fgets to get some input, it calls string to long, calls mprotect, it calls mprotect, it calls puts, it calls perror, it calls perror, and then at the very end it actually has a stack canary check. So if the stack canary dies, then it's going to call stack check fail. So there's only one function in this binary. It's not actually calling anything else baked into the binary itself, in so much as any custom functions. It's just calling library routines. So in terms of reverse engineering, this is really all we get. that's basically the extent of the program. Of course, there were some calls to library functions, but yeah, nothing else. Let's turn on the cheat mode that Mongo told me about last time. That's awesome. I love those comments. So what are we doing? What is this? Well, maybe we should run it as well. So if we just run butterfly, it says, "Thou art God, whither castest thy cosmic ray?" So you put a bunch of A's in, and protect cannot allocate memory. If we just put the number 1, and protect cannot allocate memory. If we put a bunch of 9s, and protect cannot allocate memory. Okay, so we probably want to understand what it's actually asking us for and what it's doing with it. That's resulting in this error. So just blindly messing with this binary doesn't really seem to be too fruitful. We need to dive in and understand its workings. By the way, if there's any issues with the audio, video, please give me a holler, because I'm super self-conscious that I may be streaming with the music way too loud one day and no one can actually... That would actually be a nice stream without having to hear what I'm saying, but let me know if there's any issues. So we can see we've got a sub 48 hex from RSP, which is just making room on the stack for local variables. Oh, and by the way, if you need my attention in chat, please use my name so that I get a little indicator up here that there's stuff going on. Will the video about this stream be uploaded? Yes, it will, Jimzo. If you check the description down below, there's a link to my YouTube channel. I've started uploading the videos to YouTube instead of doing just an export from Twitch. I've got totally shit tier Australian internet with a whopping 1 meg per second upload. That's 1 megabit per second. So I can't stream at a bitrate that you all deserve, but I can upload to YouTube overnight at a much higher bitrate. So check out the YouTube link, and higher bitrate stuff will be there tomorrow. So we're making room on the stack. We're moving. This is probably, I think, setting up the stack canary. Yeah, I think it's loading the stack canary from... I don't quite understand file segments and stuff, but I think this is where the stack canary is basically kept. Into racks, and it moves racks into variable 28 on the stack, which is probably just basically stack canary, putting the stack canary in place. Then it's moving, I'm guessing stood out into RDI, no, yes, maybe, and then zeroing out ESI, and then doing a set buff. So what that's going to do, set buff sets buffer modes to what's the word I'm looking for? Buffered or unbuffered, and so it'll make the stood out be unbuffered, so that as soon as you connect over the network, you actually get the stuff that it's spewing out instantly without having to wait for the buffer to be flushed. That's pretty. You see that in a lot of CTF challenges. It just makes communicating with it much nicer. Moves a string offset into EDI and puts it, so it's just printing out "Thou art God, whither castest thy cosmic ray." And then it does an fgets. So it fgetses into this, so we'll call that user input. Nope, not today, Windows. So it loads a address of a local variable into RDI, moves 32 hex into ESI, and does an fgets. So fgets is just going to get some input. Fgets takes 3 arguments. One of them is the destination for the read to be written to. The next one is the number of characters. The last one is which file descriptor to read from. So we're reading from stood in OX 32 bytes and sticking it into user input. So we're just getting some data. Then we move 1 into R14D. Sure. Then we test racks against racks, and we jump if the zero flag is set. So if racks is non-zero, we go down here. Is that right? Is that how JZ works? Test racks. If racks is 1. Oh, my brain's totally breaking on what test actually does, because it's not a compare. I think it's just going to go down here if rax is 0, because if rax is 0, then we read 0 bytes, or there's an error condition from fgets. What does fgets return? Fgets returns pointed to the string on success and null on error. Okay, so I think this here is basically just this JZ is bailing out if we didn't actually give any input. Whereas if we did get input, execution comes down here. This is where the fun happens. So we do a string to long on the input and convert, basically if we send the number 1, then the code will convert that ASCII number 1 into the actual long value number 1. So that's probably just converting our input. Oh, not converting, but convert our input to an actual number instead of being a string that represents a number. And then what we do is get the result of string to long and put it in RBX, and then move that into RBP. Interesting use of RBP. Then we shift it right 3 bits. Shift it arithmetically. So it's not a shift right, it's an arithmetic shift right, which... How does the arithmetic shift compare to the regular shift? Because I know like the regular shift works like this. If you've got 1 1 1 1 0 0 0 0 and you shift it to the right 4 times, what it does is it takes this number and this bit stream and actually shifts it 1 2 3 bits to the right. The zeros fall off the end, and then we pad it with 0. So what it does is it takes the bit stream and just shifts it to the right 4 times and makes it a smaller number. And it loses the information that it shifted off the edge. But what is an arithmetic shift? It probably doesn't matter. Does it sign extend stuff, or? Signed divide. So SAR and SHR. So this here is what I just gave a demo of is shift right. So shift right and arithmetic shift right shift the bits of the operand downward. The low order bit. Okay, so the low order bit is shifted into the carry flag, but we're not going to care too much about the carry flag at all, I don't think. So we can ignore that. So the effect is to divide it by 2 because it's base 2, so when you shift it down you're dividing by 2 each time. SAR performs a signed divide with rounding towards negative infinity. The high order bit remains the same. Okay. The high order bit remains the same. Right. It shouldn't matter anyway. So what this means is that if that was SHR, then SAR would be this. The high order bit remains remains the same. Yeah. So SAR is going to OJ, thanks so much. You beat me. Just yeah. So the high order bit remains the same. Okay. So the arithmetic shift keeps signedness because the sign of the number is stored in the first bit of a actual number value, which shouldn't affect us too much because keeping in mind RBP is coming from RBX, which is coming from rax, and rax is actually coming from our string to long. As long as we don't give a negative number to the fgets, then there should be no need to really worry about the fact that the high order bit's kept the same because it's going to be 0, so that's going to stay 0, and so we should be all good. So the fact that it's an arithmetic shift shouldn't really matter. We're just shifting to the right 3 times. OJ, welcome, good to have you around. Arithmetic keeps the sign bit in place. Yeah, thank you, Mongo. Very cool. Interesting. Okay, so we're going to take our number that was read in as a string and then convert it to an actual number. We're going to shift it to the right 3 times. And then we're going to move it into R15, and then we're going to AND it with this value. which is going to have the effect of clearing out the bottom 3 nibbles, just to make things confusing. So this is, I'd say, page aligning. OJ Mungo, do you reckon that's page making sure that the value is page aligned? Yeah, because then we're about to do an mprotect, and mprotect, I think, either requires or suggests that you give it a page aligned address. So mprotect changes the protection for the calling process's memory pages containing any part of the address range in the interval address through to address plus length -1. Okay, so address must be aligned to a page boundary. mprotect very firmly asks you to give it page aligned values. Might be an exercise for the reader as to whether stuff actually needs to be page aligned for mprotect, because I know on Windows it certainly doesn't. But maybe Linux is a bit of a hard ass about the addresses that it gets for mprotect and enforces the fact that the first argument be page aligned. So I'd say that this is page aligning the value, where the value was what we gave shifted down 3 bits. Does that sound? Yeah. Windows gives 0 fucks about page alignment. Linux barfs if you don't. Does it crash, or does it just not do what you ask it to do? With VP, the address needs to land in the page, but Linux, yeah, has to be page aligned. Thanks, OJ. Alicia, how's this hacking? Good to have you around, Alicia. What we're doing is we're trying to tackle a binary pwnable. So we've been given this this binary. It was actually released as part of a competition earlier this year, and we're making sure that we know how to. If we knew where in the world there was a computer running this software, we could break into it. So we're writing what's called an exploit for this challenge binary. So we page align. So at the moment we're just kind of digging in, trying to understand how the software works. It's the reason why we're understanding how it works is so that we can then decide how to break it and actually write an exploit for it. So we're shifting right. We're page aligning the value. And putting that in R15, and then R15 is going to then be put into RDI. We're going to call mprotect, and IDA helpfully tells us what each of these 3 arguments are. So we're going to mprotect the address that was shifted right, then page aligned. We're going to mprotect to a length of OX1000, so the whole page on a 4K byte page system. You can twiddle that on Linux, but looks like we're making an assumption here that we're going to be mprotecting the whole page. And we're going to be mprotecting it to mode 7. So mode 7 is readable, writable, and executable. So we're taking, we're basically, looks like we're actually reading in a pointer as an ASCII string. We're then doing some bitwise mathematics. We're shifting it right, and we're page aligning it, and then we're just going, all right, that region of memory is now readable, writable, executable. So I'd go so far as to say we probably won't. I mean, is this thing actually GDB? That's not what I wanted. It's not what I wanted either. Let's see what the protections on this are. So NX is on. ASLR is off. I mean, at the moment we can see that we've got the ability to mprotect an arbitrary page to read, write, execute. As long as it doesn't mprotect it back, we can use this to defeat NX. You know, if we wanted to make the stack executable, we just point this instrument at the stack, and it would just make it executable for us. But I've got a feeling it's probably going to take away the... yeah, maybe it'll take away those execute privileges later. We'll see. OJ's got it, thanks. Okay, so Linux returns an error if you don't give it a page line address. Good to know. Alicia will... Oh, you'll probably actually... responding to something OJ did. We may end up doing that. We may end up using a different payload later. We've got to figure out where to put the payload first and how to get to it. Good stuff, Atwolf. Just need the whiskey indeed. I decided to have a dry night tonight. I spent today at my cousin's 18th and had a drink there and went, you know what? I'm good for today. I feel like I need a day off. So we've protected, and we've just blasted the permissions on a arbitrary page to make it rewrite X. Then we check the return code of mprotect, and we probably bail down this leg here. Yep, and we complain if mprotect failed, and then we go here, we do the stack check, canary check, and then we wrap things up. So we need to make sure this mprotect succeeds by giving it the address of a page that can actually be mprotected. If mprotect succeeds, we come down here, and what do? We AND BL with 7. What's in BL? Okay, so RBX, RBL, oh, sorry, no, not RBL, BL, the B family of registers still contains our string to longed original input before the bit shift happened, because the bit shifting happened to RBP, but we still have a copy of this string to longed number in RBX. So then what we're doing is we're ANDing BL, so we should probably dive into what BL is. So we've got RBX, right? RBX is something like OX dead beef decaf bad. So that's what RBX can hold. It holds a 64-bit number. We know as well that EBX contains the lower part of that, decaf bad. We know that BX contains the bottom half of that, 16 bits, F bad. And then BH contains OXFB, and BL contains OX80. OJ Mongo, correct me if I'm wrong on that one. So if we were to get our original dead beef decaf bad, then the whole thing is RBX, the 64-bit pointer. Whereas EBX is just the lower half of it, and then BX is the lower half of that. This is getting kind of a bit messy, so it was the F bad, yep. So that's BX, so you can kind of see we're halving at each step, and so this is the full 64, that's the decaf bad is the 32-bit, F bad is the 16-bit equivalent of RBX. And the cool thing is you can fill RBX with dead beef decaf bad, and then you can reference it and use it using EBX, which will just give you the low 32 bits, or BX, which will just give you the low 16 bits. And then from there, we can further split it up to be FB is BH, AD is BL for the high byte and the low byte of BX. Did I get that correct? Cheers, OJ. So hopefully that is a helpful little diagrammatic representation of the mess. And this is all the same register. This is all the B family of the Intel register. It's just that either the first letter, in the case of RBX, EBX, or nothing BX, is kind of the 64, 32, and 16 bits thereof. And then BH and BL are two different perspectives on the low 16 bits. And BH is the upper byte, or the upper 8 bits, and BL is the lower 8 bits. So when we did this stringed along and put the result from RAX into RBX, then later on we talk about BL, we're talking about the very lowest 8 bits, or the very lowest 1 byte of the value. And then what we're doing is we're ANDing it with OX7. So what that's going to do is, let's say for example RBX was dead beef decaf bad, therefore BX will be equal to, can't type with this microphone in my face, OX80. Sorry, that's not BX, that's BL. BL will be OX80. Then we're going to AND it with 7. So if we were to get AD and go, you can just do bin in Python, can't you? OXAD. Yep. So that's OXAD in binary. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's fully expanded to 8 bits wide. So that BL is actually equal to OB 10101101. So if we were to do, what we're doing is we're doing BL and OX7, right? If we look over here, we had an AND of the number 7 upon the BL register. OX7 in, or just 7 in binary is, of course, I should have thought of that. So OX7 equals OB 00000111. Yep, that's right. So what we're doing is we're essentially getting, when we do BL and OX7, that's equal to this and that, right? And so when we do binary AND of entire bit streams, what we do is we basically say, as long as both bits in any given position or column, as long as they're both 1, then the result in that position will be 1. Okay, so like for all these here, we can see that in no 2 column is there a 1 in both positions, which is going to mean that we get OB 00000, right? Because we can read down and see that there's no 1s in both column. There is a 1 in both. There is a 1 in the position in both these columns here, so we get a 1. There is not a 1 in both positions here, so we get a 0. And there is a 1 in both positions here, so we get 1. So if BL was equal to OXAD, and then we ANDed it with OX7, we would get this, which is what, OX5? Oops, that's not what I wanted. Equals, that's not what I wanted either. Equals OX5. A simpler way to look at this is that the AND operation is a bit, it provides a way to mask stuff out with bits. So when you get OX anything and OX 1010101010, hang on, 10101010, what you'll get is anywhere that there is a 1 in the mask which you're applying, you're going to let the original bit shine through, so to speak. It's kind of like the sun shining through a cutout hold up against it. So you'd make a mask, like a bit of paper with bits cut out of it, and then you put it up against the window, then the sun would shine through the bits that have the cutout there. Of course, if there's no sun there, the sun's not going to shine through anything. So you're still going to get a 0 for that little bit you've cut out with the mask. But the mask will let you, anywhere there's a 0, it will block any existing bit from shining through. Anywhere that there is a 1 in the mask, it will allow the original bit to shine through. So that is bit masking. And I'm sure OJ and Mongo will catch me if I was incorrect on that. Looks like OJ's deep in discussion. So what we're doing is we are masking out the bottom 3 bits of BL. Probably up to the reader to discuss or to research, because it's not going to happen to us. But if you were to mask out the BL, does anything happen to the parts of the register that aren't covered by BL? Probably not. Probably not. But it's probably not going to matter anyway. From here on in, we're probably talking about BL and CL and that sort of stuff. So here what we're doing is we're masking out, all but bottom 3 bits from the original input that got put through stringed along. And then we put 1 into EAX, then we move BL into CL, and then we shift left CL, hang on, no, we shift left EAX times CL. And by the way, the fact that we're masking out all but the bottom 3 bits here totally makes sense, because remember before, when we shifted right 3 bits, we caused these 3 bits in question here to fall off the end of the register. So it kind of makes sense that what we're doing is we're allowed to provide a single number as input, and then the code behind the scenes will kind of go and take our input and snap it into 2 parts and deal with the bottom 3 bits differently to all the rest of the bits. So that's it's quite interesting. We're kind of giving some kind of custom packed information in the form of a number, then the program is kind of dealing with 2 parts of it independently of each other. So what we're doing is we're shifting left. So in EAX, there is the number 1. We're shifting EAX left times CL. So like in this case here, where we had BL, like if we gave the input with OXAD in the bottom byte, and we ANDed it or masked it against OX7, and we got out OX5, then what we're doing is we're doing EAX equals 1. Then we're doing CL equals OX5, right? And then we're doing shift left EAX by CL bits. So we're doing shift left EAX by CL, which is going to be OB, because EAX, that used to be, let's change this up. Oop. Therefore, EAX equals. So OX1 is of course OB 00000001. After we shift it left 5 times, we're going to get OB. We're getting if we that would be shifted left once, twice, 3, 4, 5 times. There we go. So if we were to give the input with OX, this will probably make more sense when we see where we're going with this. If we'd given OXAD in that bottom byte, and then which came out to be 5 after the mask, what we're doing is we're basically having the bit 1 with 5 zeros to the right of it. Is what's going on with this shift left. Again, it should make more sense when we get to where we're going, and if not, we'll probably come back and revisit this as we're building our exploit anyway. We then move with 0 extend the byte at RBP plus 0. RBP is currently everything except the bottom 3 bits. So it was our input shifted down by 3 bits, or shifted to the right by 3 bits, before this mask happened. So RBP is from before the mask. Sorry, not, the mask. Sorry, here. And here's another example of masking. Anything that was in the 0 position got masked out. Anything with an F in it kind of got kept. So that's another example of masking using AND. So RBP is the pointer, basically the pointer we gave in our input. So what we're doing is we're loading what is at that address into ECX. We're then XORing EAX against ECX, which remember EAX was this one that we've shifted up by a certain number of times. So we're XORing it, and then we're moving CL to RBP plus 0. Right, okay. Yep, that makes sense. So we're basically taking the output of this XOR and writing it back into memory from where we're moving entire 32-bit values with this moving of ECX, but when we write it back, we're only writing CL. So we can only kind of target a single byte, really, even though we're doing the loading with much bigger values. We're really only talking a single byte's worth of cosmic radiation affecting this here. And then we move R15 back to RDI, into RDI. R15 was the address that we did the mprotect on before. It was that page aligned address. This time we're doing mode 5, which is going to be readable and executable. And we're doing the same length as before, an entire page's worth. So what we're doing is we're making an entire page readable, writable, executable. We're inducing a single bit flip as specified by the user within that page somewhere. At the exact address that the user wanted to flip a bit, we will flip a bit for them. They need to kind of instruct what we're doing via this kind of strangely packed thing that's going to be stringed along and then snapped apart with the shift rights, whatnot. And then we're end protecting it back to... so this is going to be readable, executable. That totally doesn't store the comment where I wanted it. Ah, well. We know that... Mongo, is there a trick I can use to make this 5 be like readable, writable, executable? That makes kind of more sense. Let's put it in binary. We know that these are bit masks that represent whether you can read, write, and execute or not. So here we're taking the write permissions back off the page, so nothing can write to it anymore. And then we're doing an end protect, and then we're checking the return value of end protect. And we're going this way if it has something to complain about. Otherwise, we're going this way. We're printing the string, was it worth it? With puts. We're zeroing out R14D. R14D was 1 for a long time. We made it 1 a couple of times. I don't know why. Not 100% sure of what R14D does. And then we zero it back out again. And then we load the stack canary into racks, and then we compare what's in racks with the stack canary as per the stack. And then we do something based on the check of the canary. And if we end up down here, we wrap stuff up and call it a day. We actually return. So the user only gets one opportunity, one shot, to basically flip a bit somewhere in memory, and then the process goes away. So this is basically bitflip-as-a-service. You get a copy of the binary. You know that the binary will take some packed input. Based on that packed input, we'll flip a bit somewhere in memory, and then exit. Or not exit, return, which is the same as basically exiting. And we need to shell it. So I thought this was a really cool challenge. I had a lot of fun building this this exploit. So I'm going to do a little bit less talking, and I'm going to start putting together some Pythonness to interrogate and play with this binary, and we'll go from there, hey? If anyone's got any questions as I punch out some Python, please let me know. I'm just getting a little bit tired of talking, and I'm sure you're a little bit tired of hearing me. Sorry about that, didn't mean to knock the microphone in all your ears, my bad. It is, isn't it, OJ? Interesting that it end protects all the inputs memory to, well, it does it to RWX, and then it strips away the W, but it leaves it readable and executable after it's done. It's a cute challenge, isn't it, OJ? Aha! Mongo. Good stuff. I'm learning. I found that one. Hooray! Highlight a hex value and press B. So last week it was R, wasn't it, to get an ASCII representation? So for example, 7 we could have done R. It doesn't want to show us the ASCII value for 7, which makes sense. But we could have gone B on the 7 and yeah, gotten the bit mask there. Could have gone B on this to get a horrible bit mask. But that goes to show what that mask looks like in binary. Very nice. Is there anything else we wanted to make binary? I don't need to worry about the shift right. The protection, that's fine. That is already binary. We made that binary. The length, that's fine. Yeah, very nice. Thanks, Mongo. Yes, you did, OJ. I told you to do it many times, and you didn't listen. You didn't listen to the suggestion, but it's a good one. Alright, so I'm getting pretty good at writing this one so far. This is the little skeleton that we've been using for many of our pwnables. What I like to do is, I forgot to do this time, but first of all you set up the context of pwn, because pwn, technically this is a Docker container, and it does have the ability to pop X programs. And if you don't go and set the context to say, hey, don't actually pop a new terminal for GDB, pop a tmux split, then it kind of goes and tries to launch X terminal emulator, which is not installed in this Docker container. And I like to kind of keep everything together in one place anyway. So I like to have it all sit. Actually, I've been really liking this layout lately. Twitch, butterfly. So yeah, so it's like top and bottom, then the exploit over here. So what this will do is make sure that when pwntools tries to pop GDB, it'll pop it in a tmux split for us instead of trying to open a whole new terminal emulator and failing. Then what we do is we launch the process locally using the file name of the executable, and we assign the output of pwn.process to the variable t, which represents a tube in pwntools parlance. We then kick off an empty list for what I call the GDB command, because what we can actually do is in pwntools we can launch GDB once your Docker container doesn't stop it from launching. We can launch GDB from pwntools land. We can specify first of all the tube to which we want to attach to the process on the other end of, which will be the butterfly process. We can also supply a script, a GDB script that will be executed on GDB starting up and attaching. So what I do is I usually have a script that starts off with just being, this is a fancy way of having a string of the letter C and nothing else. But what we can do is we can, there we go. We can go and have multiple commands here like doot and break on main, and what it'll do is this here will stitch these together with new lines in between them, so that we can have a new line delimited script for GDB to execute upon attaching. The reason why I do it this way is because without fail I always forget to put new line at the end of each of these, and with this here it does it for me. So that's the way I like to do my GDB script. We then pop GDB and attach it to the stuff on the other end of the tube and execute the script, and then we just return a little interactive shell to the consumer of the exploit so that they can sit there and do dumb stuff like sending the number 1337 and getting this error here. We saw this error. It's probably from this failed mprotect, because the address 1337, part of which will actually be the low 3 bits of this will be which bit, what address to be flipping, but we're failing with the mprotect, and so we're going down here and complaining and returning. That one indeed, OJ. We didn't check whether there's Stack Overflow. No, we didn't. It was bounded though, being fgets. Are you telling me that there is? We go and get how many characters? OX32. Yeah, no, we got plenty of room. Plenty of room between the user input and the stack canary. And there's no other local variables we can smash anyway, so Good call though, Mongo. I'm a jerk and I knew where the bug was. And I also am a idiot who makes assumptions that he shouldn't be making. And I assumed that that wouldn't be there because I'd already seen what the binary was. Yeah, well, Tmux is so much nicer. I love the vertical and horizontal splits. What else do I like about Tmux? I find its copy-paste mode to be nicer. I find its status bar. The status bar and screen's not too bad. But yeah, no, I'm a huge Tmux fan. I get sad when I'm on a server and there's no Tmux and I have to use screen. The switching is the hard part indeed. And you get a little bit stuck when you then have to switch back temporarily. But yeah, it's definitely worth switching. If you double click the stack variable name, you get a nicer stack frame. Oh my... I need more of you in my life. Yeah, nice. That's cool. Actually, Mongo, we should probably hang out here for a little bit. We should change the type of things like user input. Instead of being a whole bunch of bytes, we should actually make it an ASCII string. Maybe. Mongo, how would you set up this stack view here to actually better represent what user input is and what you know stack canary to be? I mean, what's R? R doesn't come up here, but it comes up in stack of main. Mongo, would you do any tweaking on this that may be helpful in more meaty functions? You call it an array. Alicia, yes, I'm using Ursi to see the chat. So what do I do? Change to capital A. Just click on this and go capital A, capital D, capital A. This here, D, D. Shift star to make user input an array. Oh, okay, sorry, yeah, I was making it ASCII, not... I saw A and was like, yeah, A for array. Shift star. Convert to array. How many elements? Well, we can probably go here and actually, for the number of elements, have a look at how many characters got fgets, which is OX32. Is this here decimal? Well, oh, that kind of makes sense. Somewhat, maybe, because we know that it wasn't actually using the full space allocated to it. Interesting. I might have a play around with the stack view and learn how to actually set data types properly. Thanks for your help, Mongo. Let's get into actually interfacing with this bitflip-as-a-service API. So we know we need to send a ASCII representation of a number, because it then gets put through string to long, and then we know that it carves off the bottom 3 bits to actually do the decision as to which bit to flip. And then uses all the rest of the bits as a pointer for the byte within which to do the flip. Yes, byte within which to do the flip. So what we might do is just define a function that directly uses t, because t here is a global variable, so we should be able to access it from functions. Def flip bit. We want to take in the what do we want as an argument? Target byte, or the pointer to the target byte, and the target bit. Can we access t from within here? print T? Or do we need to actually reach out and get it from the global scope? Flip bit 1 1. I'm not so good at the Pythons. Yeah, we can like reach out to the tube from this scope here. Cool. So how are we going to flip a bit? We're going to take in 2 numeric inputs in Python land, and then we're going to stitch these together into a single number, and then get the ASCII representation of that number and send it down the wire. So how are we actually going to pack this? So we know we need to send something like this. We need to send as a bit pattern, we need to send 32, actually we need to send 64 bits because it's a 64-bit process. So we want to go 64 append, nope. Yep, fucked that up, didn't I? 64 append. We want to send a bit pattern that looks like this. 64 bits worth of the target byte, and then 3 bits that represent the target bit, because the 3 bits is then how much the 1 gets shifted to the left by before it then gets used in the XOR. So we want to send something that looks like this as a bit pattern, so we need to actually pack these 2 values into a single number, which means that we should just be able to shift this up by 3 bits and then add that. Yeah? Gotcha. Thanks, OJ. I knew there was something you had to do. Do you also have to refer to global T if you want to write to it, or can you write to globals without actually saying global T? Oh, we get bitwise operators in Python. Is it going to be like this? I'm going to go Python. Let's go like 1 shifted left by 2 in binary. Yeah, that's how you shift left in Python. You just do arrow, arrow. Yeah, returns X with the bits shifted to the left by Y places. And new bits on the right hand side are zeros. Oh, it's the same as multiplying X by 2. 2 to the Y. Yeah, that makes sense. Just, you could use multiplication. Mongo, that's a good question. Don't use globals because they're awful. Yes, I shouldn't be doing what I'm doing. I should, OJ, I probably should be passing in T to this function here. I should also be programming functionally and probably not actually mutating state at all, but YOLO. Yeah, Mongo, the stream's 15 seconds behind, unfortunately. I've had a look into it and it seems like there's no way to actually reduce it. You can only make it worse, if you, which for some people is worthwhile on Twitch. You kind of don't want people to see what you're doing in games and then know where you are in the map, so you kind of delay your stream by 10 minutes or so. But yeah, unfortunately there's a 15-second delay that we can't defeat. Also, I'm lazy and don't check the chat as often as I should, so you may have sent it, I may have gotten it, just not read it. Alright, so we can shift like this. So really, as far as the number we want to send it, do we just shift target byte to the left by 3 bits? And then either AND or add, we can do either or because these bottom 3 bits will be 0 after the shift. Add the target bit just as a number. I think that's all we do. I think really we just do this. T.send line, the string that is pointed to target byte, shifted left by 3 bits, plus target bit. And we'll go and wrap this here in brackets so that we know what's happening and order of operations isn't screwing with us, even though I'd assume that the shift left would have higher precedence than the addition. I think that's really just how we flip a bit, but now we've got this nice little API that we can use to interface with it. So for example, let's, because ASLR is off here, ASLR is off. Let's flip a bit inside this string here. Thou art God, God, whither castest thy cosmic ray. By the way, the whole cosmic ray thing is because cosmic radiation can induce bit flips in can induce bit flips in any memory. It's just that ECC memory can catch it and do stuff with it. So let's get this address here of this string. First of all, we can go GDB butterfly, we can start it, then we can examine one string at that address, oops, and we can actually get the string back, and then we should be able to induce the bit flip and then ask GDB to show us what the new version of the bit is, or the new version of the string is, I should say. So I pointed to thou equals OX that. Did I stuff that up? Nope, that's right. I just fat fingered that. So pointed to thou is that. We probably also want to quickly pinch. We should get the address of this return and set a breakpoint on it so that we can actually, within GDB, see what happened to the program before everything goes away on us. So I'll just grab this here and do pointer to main ret equals OX that, and append to our GDB command to break at the address star plus pointer to main return. That should get us a breakpoint on the return from main. So what we want to do is flip bit in the string within the byte at pointer to thou. If we just kind of target that first byte, we should see the impact of our flip in here in the T. So we'll just target the first byte for now. And which bit do we want to flip? The third one. Let's see what happens when you flip the third bit of capital T. So we'll save that. We'll quit that. Don't need that anymore. And we'll run the exploit. Ba-bow. Cannot concatenate string and integer. Let's do this. And actually format it. It'll then cast it properly for us. Alright, so we get the message, thou art God with a castest thy cosmic ray, and then we get was it worth it, and then we hit our breakpoint. So now we should be able to examine one string at the address of the pointer to thou, and we get backslash HOU art God. Cool, we can flip bits. For funsies, let's flip the bit at pointer to thou +1 and flip the third bit again. Run the exploit. We get our message, If we examine the string again, then yeah, we can flip the third bit in capital H at the second character of this string here. Just to kind of double check our work. So we had capital H, and then we turned it into an at by flipping the third bit. If we go man ASCII and get capital H, it is OX48. We go Python, we get the binary of OX48. Looks like this. If we were to get the hex of that, and we'll go and flip that third bit manually. Ooh, do I have an off by one error here? I think I do. I think I've got an off by one error. Let's flip what I thought to be the third bit, and we get OX4C. If we then do the character OX4C, we get capital L. Aha, yep, cool. If instead of flipping that third bit, we flipped the fourth one and changed this 1 to a 0, then we get OX40. The character at OX40 is at, yep, which is what we actually did get. So we've got a bug. We've got an off by 1 in this target bit here. What we want to do is we actually want to subtract 1 from the target bit, because see, if we have a look at the code, this is where so we put 1 into EAX, and then we shifted that number 1 up by the number of bits as per the bottom 3 bits of the input. So EAX was already pointing to bit number 1. I guess it depends on whether you zero index the bits in a bit string and your idea of what is the first bit. You know, for example, this binary string here, this number 0, is that the first bit or the 0th bit? Is this the first bit or the second bit? So I guess it kind of depends how you see your binary and how you count your bits. We'll stick with what we've got. No. I'm going to confuse myself because I naturally think of bit strings as this being the first bit, that being the second bit, and that being the 8th bit. I don't think in terms of 0th and 1st, like you do with arrays, which is probably an immature way of thinking on my behalf, but that's just how I roll, and if I don't fix this, I'm going to get really confused. So let's go and define flip bit. What we need to do is the target bit, we need to subtract 1, because it's already at the first position even when you send 0. So if we quit that, if we flip that third bit of the second character in that string again, then we get capital L. So we already had odd capital. We already had H. We get the binary for that. And we get this. If we flip that third bit, well, the way I kind of think of bit number 3 as being this bit here, and then we get the character as per that, we should get, was it capital L? Yeah, capital L. Cool. And we did end up getting capital L. So now we've actually written a little function that will interface with basically the bitflip-as-a-service API, and will let us flip a single bit somewhere in memory. So that's a start. Now we need to think about which bit where we're going to flip. It may be the case that we could basically get a shell with a single bit flip if we knew exactly which bit to flip. But that's not how I solved it last time I solved it. I haven't read any write-ups. Maybe there is a single bit out there that you can flip that's just going to be like the insta-win headshot bit. But the way that I achieved this was basically because I mean this program, you only get one shot to actually flip the bit. The way I solved it was to think of a way in which I could flip multiple bits and get multiple attempts at the whole bit flip API right here. So I'm going to take a quick 5-minute break. It may be a good thought exercise. Have a think. How would you get to the stage where you could use this API to flip more than just the one bit? Alternatively, if you only had one shot, which bit would you flip? If you know of the bit that actually is like the insta-win, headshot, get a shell, win everything bit to flip, good stuff, because I can't think of one. Have a think about how you would turn this into a multiple bit flipping machine. I'm going to take a quick 5-minute break. If you need to take a break, now is the opportunity, and we'll be back in about 5 minutes for working with this and doing cool stuff and hopefully getting a shell. So I'll see you in a second.
Like a Hellcat. Like a hell. Like a Hellcat.
Alrighty, let's get this show back on the road. Yeah, simply, I'll hook you up with the explanation in a second, but Jim, at Wolf, and it was at Wolf, Jim, someone else, I think someone else might have said they enjoyed the streams. Thank you so much. I really appreciate the kind words. Knowing that people enjoy hearing me rant makes my heart very happy, so thank you very much for the kind words. I really enjoy doing these streams, and to hear that people enjoy them makes it just that much sweeter. Let me just catch up. Yeah, Cosmic, thanks so much. Appreciate that. So, simple. I'm going to call you Simple, if that's okay, Simple. Simple, what we're doing tonight is working on a pwnable called Butterfly. So it was actually, I didn't say this earlier, but it was part of the CSAW CTF earlier this year. There's a link in the description to this page here This page here has the challenge briefing, which is very cryptic. It talks about butterflies, and now that we know what we know why it's called butterfly, because when a butterfly flaps its wings, something on the other side of the world can go wrong, which speaks as to the kind of theme of the challenge. But we get this very cryptic briefing, and we get told that during the competition at butterfly.pwning.xxx on port 999, there was the challenge server running. So during the competition, you could connect to that server there, and that server was running this binary, butterfly. That's really all you get told in the briefing. So what we've done is we've loaded the butterfly binary into a reverse engineering tool, a disassembler called IDA, and we've made sense of the one and only function in the binary and understood the fact that it prints out some messages. In fact, we can probably see them here. Yeah, when you connect or when you run the binary, prints out the message, "Thou art God, whither castest thy cosmic ray?" And then you need to send some data to the server. So what you need to send is a specially packed number as a string. Then what the server does is, with all this code here that we've gone through, and I've done my best to explain, the server will basically convert that string that you sent into a real, actual number, do some bitwise mathematics to it to basically split it into two parts. First of all, you've got the bottom 3 bits, which we use down here, and then the rest of the bits get used up here. Then those bits get used to basically change the memory protection on the page of memory that the address you gave lands within. So you supply two things. First of all, you supply an address. Second thing you supply is a bit count. So the address gets rounded off to the bottom page boundary, and then that entire page gets protected to be readable, writable, and executable, so that the process can then read the memory, write to the memory, and execute the memory. So the protect happens. After the protect, some more bitwise math gets done involving the bottom 3 bits of what you send. What it then does is it then looks up as a pointer the exact address you gave. So not this, page aligned version of the address, but the actual byte address that you gave. It loads the byte, or actually loads 4 bytes, but we're really only going to worry about the 1 byte that it loads into a register. Based on those bottom 3 bits of the input you gave, it then flips a single bit in that byte. So a 1 becomes a 0, and a 0 becomes a 1. You get to pick a single bit and flip it. It will then write that byte back to memory. It will then do another protect to set the page within which that byte is located to be readable and executable. So up here it makes it read write X. Here it just makes it read X. So the process wouldn't be able to write to it anymore if it tried. And then we print out a message and then we return. That's all the binary does. We now need to think of which bit in memory do we flip so that we could hack into a computer running this as a service. And that's where the challenge comes in. And we get to build an exploit that will shell a machine running this binary. So that's what we're doing tonight. Where are we? Where was the question? So that's what we are doing. Simple. Mongo mentioned the flare-on challenges. Let's have a quick look at the flare-on challenges. 3rd annual flare-on. Okay, so it's done by FireEye, that's right. Reverse engineering. So it looks to me like the Flare is the FireEye Labs Advanced Reverse Engineering team. So flare-on is a series of reverse engineering challenges, 10 challenges. The first 10 challenges prior to November 4th got prizes and shout-outs on the website. Cool. So yeah, it looks like it's a series of reverse engineering challenges, which, hey, might be a really good topic to be streamed sometime soon. Maybe we should add the flare-on challenges to the list of topics. So thanks, Mongo, for the reminder that flare-on has come and gone. So that's what we're doing. Atwolf's been late to work 3 times. They're just too interesting. I'm really glad you enjoy it. Thanks, Atwolf. So there wasn't much guessing involved. Yeah, cool. I hate CTF challenges where there's trial and error and guesswork, and especially where there's stego. I don't like crypto, but I hate stego even more. Reversing's cool. I'd like to get better at reversing, so we should definitely check out the Flare On challenges. Oh yeah, the Matasano crypto challenges as well. Thanks Infinite. The Matasano crypto ones are really good. If you haven't done crypto, do the Matasano crypto pals challenges. They're a lot of fun, and I learnt a lot. I think I'm like halfway through the block cipher, the block crypto one, because I got lazy. I should go back and do more. In fact, maybe we should do it on stream together. Might be interesting. So good call, Infinite. There's so many good challenges out there, so many things to do, so few hours in the day. What else have I missed? Book list, hey? OJ's got a book list. I should check out OJ's book list. In fact, I'm going to bookmark that in my personal browser and check it out later. Bookmarked. Okay, you need to sign in. Cool. I'll check that out later. Jess Pixel, good to have you around. We're doing a whole bunch of, or not a whole bunch of, we're doing a binary pwnable tonight, so I hope you enjoy it. I hope you caught the briefing I just gave Simple on it. If not, there's a link in the description to the challenge we're doing. Yeah, cool. Hope you enjoy it, Simple. Hope you learn some stuff. Cool. None of us know everything. There's always stuff for us all to learn. So indeed, OJ, we're all here to learn. So I have done this one before, and I found it so much fun that I wanted to stumble through it on stream. It's been a couple of months since I've done it, and when I did it, I wasn't being viewed by people. So let's see how I go with an audience. All right, so back to the challenge, hey. I think actually I threw the question out, which bit would you flip if you had... every time I think you've got one shot, I think of that that Eminem song, Lose Yourself, the intro to... That's what I think of. I think OJ was saying that he would flip a bit in the save return pointer. Yeah, which is where my mind first went. But then I... correct me if I'm wrong, but the save return pointer... First of all, even though the binary is not ASLR, the location of the stack would be. So without an info leak, you wouldn't know where the save return pointer is. But where I think that would really screw you is the fact that the process later on emprotects stuff to make it. I thought about this one while I was off stream. It emprotects it to make it not writable. So your stack just became subject to read only. I think that would make for a very sad time. Apart from that, flips in the GOT sounds interesting. Maybe we'll end up there shortly. So let's see how we go, hey? Alright, now I've got to actually think about which bit I did flip last night. I think what we want to do is we want to get to the stage where either we know a single bit somewhere in memory that can be flipped, and it's like a headshot bit, and basically you flip that bit and then it's just game over. Barring that, we really want the ability to flip more than one bit. Because if we get the ability to flip 2 bits or 3 bits or 20 bits, our options would really grow as to where we could go with this, and we can probably think of a few different places that we'd like to flip more than just the one bit. I think I might, let me just give me a second. I'm going to go to BRB just for a second. I'm going to adjust my microphone because I think it's drooping a bit throughout the night, and I don't want to bang the microphone while I do it and send awful bang noises down the line. So I'm going to go BRB for just 1 minute while I fix my microphone stand. Give me 1 second. Alright, it's a second-hand microphone stand off of the Australian equivalent of Craigslist. It was cheap, but I reckon it's seen some shit. So it's not up to the standard it once was. But it was like $15, so I'm not going to complain at all. Actually, I'm going to complain a lot. How do we get more than one bit flip out of this binary? I'm thinking if we were to, because we can flip any memory, because this emprotect up here is going to make sure that it's writable at the time of the flip. So we can actually flip bits inside the program code we're not limited to the writable areas like the stack or the GOT. We can flip bits inside the program. So is there a bit somewhere inside main that, if flipped, would cause main to infinite loop? Because that would be cool. If we could just get main to basically loop back on itself by flipping a bit somewhere in this function, we'd be gold. Because then we'd be able to just repeatedly get this message, thou art God, whether castest thy cosmic ray, and we could just keep on providing those packed values as to the interface to the bit flipper. We could flip more than one bit, and we could basically flip our bits somewhere in memory that pertain to our shellcode, and then flip some more bits inside probably the program code to divert execution across to that shellcode. So if we can just find a single bit somewhere in here to basically cause the program to loop, would be sweet. So I'm thinking it's got to be somewhere after the actual XOR happens, because if we caused it to infinite loop before that XOR, we wouldn't get the ability to flip more than one bit. So it needs to be somewhere, probably along the program path, the path that actually execution goes. So either somewhere in here, or here, or here, we need to flip a bit that causes the program to loop. So where could we do that? It's worth checking. Can we smash this canary? So we can smash this canary and cause this J and Z, which normally does go here, to this 883. If we can cause this 883 to become a bit flip that then takes us back up to here somewhere, then as long as we kill the canary, we're going to kind of follow this green arrow, but we can make this green arrow point up to here instead. Can we kill that canary without actually having to cause a bit flip within it? Because we only get one shot. We probably want to flip a bit in here, in this address here. If we actually go to the hex view. Right. Okay. That address isn't actually encoded as the operand in full. It's probably just a relative offset. So maybe that won't work. Can we kill a canary? We can do this really quite trivially, actually. Let's quit that. Let's go Python -c print a times 1024 into butterfly. That didn't work because we actually got the error. Mind you, we got the error probably from this here, and then does p-error actually exit, or does p-error just print the message and then return? Does p-error return? Yeah, I think p-error does return. So really we're seeing this return come down here, and if we were to print 1024A's and shove it down the gullet of butterfly, we don't get a stack failure. Sad face. What if we keep that breakpoint on the return, instead of sending that flip bit, go t.sendLine a times 1024 and run the exploit. I commented out the whoops, the variable, not the actual flip bit, based on the variable. Whoops. Alright, so if we send 1024A's, then we do get our breakpoint set on the return. So the stack failure didn't end up happening. tally $RSP minus 30 minus 8 16 32. Where are my A's? Yeah, cheers. Thanks OJ. I've never heard of IDA before. It is super powerful. Options, general number of opcode bytes. The opcode's next to the instructions. Doesn't work in graph mode. I'll be the IDA tips guy from now on. Mongo, if you're cool with that, I am super cool with that. Yeah, IDA's great, but it's not cheap. OJ is probably about to say that the first point of call maybe should be Binary Ninja. I've heard a lot of good things, and OJ actually has experience with Binary Ninja. I think OJ would love to talk about his opinion of Binary Ninja, because I would love to hear OJ's opinion of Binary Ninja. Because yeah, IDA's a bit exy. Binja is a lot cheaper. And Binja is more or less, at least for the beginner, a totally equivalent tool to IDA. I think IDA's got some more advanced stuff that helps people who are a bit further along, but I'm not that kind of person. I bought IDA back before Binja came out, so now I'm just kind of stuck in the hole of paying maintenance and trying to justify, and getting to the stage where I can justify the feature set of IDA versus Binja. But if Binja had been around when I bought IDA, I may have bought Binja. It looks super attractive. So yeah, P error does return. So I don't think we've got a stack buffer overflow. User input is at minus 68 hex. Stack canary is at minus 28 hex. We can only kind of afford to give in the fgets OX32 bytes worth of data. So yeah, we can't, can we? No, we can't touch the canary. So we can't cause this JNZ to be taken, so we can't go and fiddle with this here. What else could we fiddle with? Sometime after the writing back of the... Here, the writing back of... We have to flip something down here that does give us an infinite loop inside main. That's what I want. I mean, there may be a different way of doing it. Like maybe main's parent. If we flip something inside main's parent, can we cause main to happen again? Probably not, because after the call to libc start main, which takes this address in RDI as an argument, we just get a halt. So I don't think we can flip anything inside that halt to give us an infinite loop. Where else can we cause main to loop back on itself? Oh, hang on, there was a mandatory IDA tip for me. Options, general, number of opcode bytes. Options, general. I should just go through these IDA options because there's so much stuff in here I've obviously missed. What am I looking for? Something number of bytes. Options, general, number of opcode bytes. Options, general. Is it on a tab, or am I not seeing it? Pellets, that's what I pay them for. I actually don't pay my mods, so I don't get any wrong ideas, but if I was to pay them, I'd be paying them to be super abusive. Good to have you around, Pelias. Welcome. Pelias is a good lad. If anyone hasn't had the privilege of meeting him, I am so sorry. Pelias is a good sort. It's on the first page. I'm just blind, hey? Number of opcode bytes. Ah, there it is. Number of opcode bytes graph. I thought it was like I was looking for a tick box, thinking there was a tick box to get it to tell me how many bytes was in the opcode. That so if we go and put like 8 in here, it's actually going to show us 8 opcode bytes. That's wicked. Huh. That's what I need in my life. That's yeah, big fan. Does it tell you if it's truncated? Like if we go, I did not want to hit that. I did not want to hit that button. If we were to go like number of opcode bytes 2, does it tell me about truncation? Yes, it gives me a little plus to let me know that I'm not seeing everything. That's wicked. Thanks so much, Mongo. Right, okay, so which bit do we want to flip inside all this to give us our loop? . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Indeed, and Peleus, indeed. That's I love that. That's one of the features that I've got to look it up now. You go binary.ninja, and one of the first feature they brag about having. Like, I love IDA, don't get me wrong. So anything that I hang on IDA, I don't dislike IDA at all. IDA is a fantastic tool, and I am very happy that it's in my life. But you go to the features of Binja, and the first feature is undo, because who hasn't lost info without undo? IDA does not have an undo function. It's one of its few pitfalls. I'm sure there's many pitfalls, but it's one of the few that everyone likes to hang shit on it for. So I love that Binary Ninja just like salt in that wound. But yeah, IDA is a good tool. It's just fun to make fun of stuff. How do we get our loop? How do we get our loop? How do we get multiple shots at the flipping of bits? Ooh. What if we fuck with this? If we were to mess with this, we could actually influence how much the stack gets rewound by. We may be able to cause the stack pointer to point within the data payload in time for the ret. Huh. So if we flipped a bit inside OX48, we could actually probably reduce how much of the pivot, because we do that, we go pop, 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 ret. The other thing is, how does, we should look into is, how does string to long work? Like, can we put a whole bunch of garbage after the number and have that garbage written to the stack, but ignored by string to long? Because that would actually probably just give us rip control. And with rip control, we can either cause the return from main to loop back to the start of main. We might want to avoid this sub RSP OX48 here, just so we don't have a stack overflow. Not a stack buff overflow, but a stack overflow. In the case of flipping enough bits on a system with a sufficiently limited stack, we might want to avoid that. But with rip control, yeah, we could either make main loop back on itself, or just use rip control to do cool shit. That might be the way to go. See if we can mess with this OX48 to cause, yeah, the stack to be unwound not enough and land within our payload. Let's try something. Toggle the negative bit that would send you to the other end of memory, and crashy. Which bit are you talking about, OJ? The negative bit in where? In the meantime, I'm gonna have a bit of a poke at string to long and see if we can include some garbage inside this t.send line and still have our bit happen inside the pointer to thou. So if we were to go string of all that, you know what? Let's make this here a little bit less disgusting. Let's make the payload be pointer to the target byte, shifted left by 3, payload plus equals target bit minus 1, payload equals string of payload, t.send line payload. It's a little bit nicer. Yeah, okay, gotcha. Well, convert 48 hex to negative 48. You're talking about the stack unwind, hey? That could work because add is signed, yeah. If you made that negative by flipping the sign bit, wouldn't you cause RSP to be subtracted from? I mean, it wouldn't do us any good, But you wouldn't send RSP to the other end of memory, would you? Because you're adding a negative number to RSP, wouldn't it just move RSP up the stack? Not that it's any good to us, but you'd still keep it within the stack, wouldn't you? Fgets reads. So Fgets will accept a null byte, will it, Mongo? Yeah, nice work, Mongo. Thanks for that. Yeah, long jump. Okay, long jump, right. Yeah, no, it's actually the sub the add RSP. This is the 48 I was looking at. Maybe you're thinking about a different number somewhere else. But that's a stack unwind. I'm gonna go payload plus AAAA. Let's just see if this works. Let's quit that. Let's run the exploit. Let's look at our string. So we still got our bitflip, even with 4 A's in the payload. So yeah, Mongo, you're right. We could have used that null byte, because fgets will eat a null byte happily. Right? Fgets will read a null byte. Is that what you're saying? Fgets will accept a null byte? Man, fgets. Reading stops after EOF or a new line. Yeah, so it looks like it's happy to read new line. So yeah, we could have actually null terminated the string, so that stringed along wouldn't be eating our garbage. But it looks to me as though stringed along will happily have at least alpha garbage after the number. If there was a number there, obviously it would change the meaning of the number, and we'd be in for sad times. So maybe the null byte is still worth putting there as kind of like a guard against possible numeric data in this garbage. So null byte's probably a good idea. Thanks, Mongo. Does it still work? Do we still get the... Yeah, we still get that. And I'm guessing our A's still got written into memory. Why was I checking the stack for A's or what? Oh, that's right, because I was actually sending A's. Cool, so we should be able to do that. Let's do payload plus equals null byte, and then payload plus equals A times OX. How many characters does the fgets take? It's going to take OX32 minus 1, because it's going to actually null terminate the string for us, so we can only send OX31 bytes. So let's go A times OX32 minus 1 for the null byte, for the null terminator, minus the length of payload. So let's go and fill that sucker up with as many A's as it will take after the numeric data. So we've got a whole bunch of A's hanging out on the stack. So if we send that, we can still flip that bit in that string. We should be able to do tele RSP minus 16. We should see these A's on the stack. Am I going the wrong direction? Ah, there's our A's. Yeah, we've got a bunch of A's on the stack. Okay, cool. Yeah, that's where I'm going, AJ. You reckon toggle the 4 to a 0, hey? Where are we? You reckon change that OX40 to OX, or OX48 to OX8? If we go and have a look at that in the hex view. So you reckon change that 48 to 08. Is that only going to... Oh, we've got a couple of pops still to go. So that should basically lend us... Yeah, I think that'll give us rip control. I think you're right. So it's going to be at 61, 62, 63. So we're going to flip the bit. Let's go. So that's the pointer to there. Pointer to sub ESP. No, it's an add ESP, isn't it? Add ESP amount equals that 3. So the pointer to the amount that we're adding to ESP in the function prolog, or epilog, sorry, for main is at... That song just played twice. What are the odds? Must have looped on the playlist. So, yeah, it's at 60, 61, 62, 63. So it's in this byte that we want to do the bit flip. So what does OX48 look like? Yeah, you only get one flip, Peleus. Do I know how to printf floats in assembly? There you go. OJ's the man to ask for building stuff. OJ's also the man to ask for breaking stuff. I don't know why I'm the one streaming. I'm doing the best I can. But yeah, OJ's definitely the one to ask for. Yeah, %F sounds right to me. Cheers, OJ. Yeah, Peleus, you only get one flip, but we're trying to turn it into multiple flips by either inducing an infinite loop inside main using our bit flip, or getting rip control and then inducing our own infinite loop by setting rip to point within main. So that's what we're working on. So we've got like OX48, Python OX48 in binary, looks like this. So we want to flip this bit here so that we just get 8. So it's the first, second, third, fourth, fifth, sixth, seventh bit. Really? Yes, really. 7th bit. Really? 1, 2, 3, 4, 5, 6, 7th bit. Okay. So pointed to the add ESP amount is that. We're not going to flip the bit in thou anymore. I had like this shit ton of A's in there the whole time. Don't need that anymore. Lucky didn't break us. So we're going to flip the bit at the pointer to the add ESP amount. We're going to flip the 7th bit, which should make that add ESP add 8 instead of 48, which should result in the ret hopefully returning to 41414141 41414141. Let's see. Cross our fingers. Run the exploit. So we hit our breakpoint on the return, and yeah, at the top of the stack is a bunch of A's. If we continue, we get a seg fault on the return. Rip doesn't actually have the A's in it, but we can see that the stack points to a bunch of A's. Just. Oh. Hang on. Oh, that was close. We've just got rip control. Just. Alright, so what we can do is control rip. I don't think rip control gives us much at the moment because we've got no really great way of writing an executable payload. Is there NX on? Yes, NX is on. We don't have a executable payload in memory, although it's 64-bit. If we knew the layout of the victim's ASLR and we had an info leak, I'm going to rewind that. If we knew the version of the victim's libc and we had an info leak to tell us where it was, there are some insta-shell gadgets inside the 64-bit libc. But we won't go down that path tonight. I think we'll just use our rip control to return to the top. Do we want to return to the top of main, or do we want to return to... It's probably safest to go to the top of main, because if we return to after this sub RSP 48 hex, then we're probably going to run off the bottom of the stack quicker than we'd run off the top if we left it in. So we'll return to the top of main. You know what? We'll return to near the top. We'll return to the address of this sub. We don't care about these pushes. We don't care about saving the value of registers because screw the parent, they can deal with the loss of registers. We're not going to let the parent get control anyway. So we'll just go straight to the address of the sub RSP 48 hex. I think that's what we're going to do. So I'm going to work on anyway. Let's nail this SRP. Well, not really SRP override, but let's nail our rip control. Instead of doing a bunch of A's, we'll do pwn.cyclic. That. We don't need the extra brackets. We'll just do pwn.cyclic to the extent that we can still fit characters in. What have I missed? I saw a doot a second ago. One in 30 odds. Wasabi, good to have you around. Have you checked, like, because I did publish that playlist. Did you go and look up the playlist and get the length of it and figure out what the odds are? If so, that's totally cool. Twitch, music. Yeah, I think I've got 34 files. Actually, this directory is being shared. Work, Twitch, no, not work, Twitch, music. lsstar.mp3, body count list. Nice work, Wasabi. Nailing the statistics homework for us. Good to have you around, dude. Thanks for dropping by. Alrighty, let's. What are we doing? That's right, we're nailing our rip control. So we've got pwn.cyclic. Yeah, thanks, Wasabi. Yeah, I do have that. If anyone hasn't noticed, if you like my garbage music, I've got a playlist hosted on my GitHub because I felt like the people who make all the music is, I think, either Creative Commons or just plain old NCS. No copyright sounds says you can use our stuff for streaming and YouTube, so I'd go and yank their stuff. But I thought the authors of that music deserved the proper props. So if you want to give them props and check out their other stuff, go check out the playlist and check out their records and whatnot. Let's nail this rip control. Go, exploit. I'm just going to jam a cyclic pattern in here. We'll continue. Grab that there. And we'll do payload plus equals a times pwn.cyclic find. That's a string. Oops, that's not right. I needed to do pwn.cyclic n equals 8 to ensure, because it's 64-bit, we need to do n equals 8 for pwn.cyclic to make sure that every 8 characters are unique. There we go. Payload plus equals a bunch of padding. Pwn.cyclic find. Cyclic find. That n equals 8. We don't need that anymore. Payload plus equals pwn.pack64. Rip. We're going to take a new argument, which is going to be rip, which will be an integer. And we'll send that. Yep, that looks good. So we're going to do a flip bit of pointer add ESP amount. Flip the 7th bit. OX 42, 42, 42, 42. Cool. Let's go and return to BBBB to see if the rip control is sorted. Continue. Hey, ooh, new line. That's not what I wanted there. That's not cool. That's fine. It's just showing us a string representation, but the first 1, 2, 3, 4, 5, 6, 7, 8 bits of it, 8 bytes of it, are the pointer BB. So we should be fine. So that's rip control sorted. So what we're going to do is we're going to get a pointer to this sub RSP, which was here. And we'll call this pointer to mainish. Because I'm imaginative like that. It's mainish. It's almost main. It's a bit after the beginning of main. So pointed to mainish. So let's flip the bit inside the amount that we're adding to ESP at the 7th location, which is going to guarantee us rip control from now on. And the this should work. This should work. And we're going to return to pointer to mainish. And then we're going to flip the bit inside the pointer to thou. So we should get 2 shots at this bit flip in this case. I should probably be eating these prompts at some stage. YOLO. When we go t.interactive, we're going to get like a whole slab of prompts and banners and stuff. We should be fine. Let's run this exploit and see what happens. Bow. Bit flip takes 3 arguments, 2 given. I just needed to update the bit flip of the pointer to thou with the return pointer that we desire. Run the exploit. So we get 1 breakpoint, which should be on that first instance of the return. We get a second breakpoint, and we get another banner being printed out. We continue again. And there we go. The prompt actually changed so that we have done this second bit flip and flipped a bit within the string of the thou art God string. And we get another shot. It's asking us for more stuff. This is cool. So if we cancel that and quit that, and we bit flip the pointer to thou, if we just keep flipping the characters, bits in characters of that string, and run the exploit, you know what, let's quit that, let's get rid of that. I can see there's stuff there, but I'm going to ignore it for now. I'm going to get rid of this breakpoint, and we're going to reset, and we're going to do the big reveal this way. Run the exploit, and yeah, what we get is, this is the banner that was printed when we first connected. And it was the banner that was printed for the bit flip in which we flipped the bit within the amount that we add to ESP. Then we got this banner, which was the banner we received before we did this flip here. And then we got this banner, and you can see we're starting to actually progressively flip more and more bits inside that string. So we've now got a opportunity to flip multiple bits. We need to keep in mind that we have broken the program. It doesn't return properly. But we've got rip control on each instance of the flip that we do, so we may end up using that to return later on to somewhere else in memory, at which we have basically, I think what we're going to end up doing is painting shellcode into memory using bit flips. And then we can just use our rip control to make sure that we return to the painted shellcode. So that's kind of cool. I think we're almost done with this. Parks, good to have you around, dude. Welcome. I think it's been a pretty cool night. You should probably check out the video if you're craving more of this. I've really enjoyed it. What we've worked on is a binary called Butterfly. It's basically bitflip-as-a-service. So how it works in essence is I'm really loving the no stack buffer overflows. I reckon there's just so much cool stuff out there that so many people just don't move beyond the stack. I mean, it's so important to start with the stack buffer overflows, but there's just a world of really cool stuff out there. It's a single function program, so it's a tiny little program that basically reads in a packed input, a numeric input, and that numeric input then gets broken in two by the program. You can go through and look at the shift rights and the shift lefts and make sense of how it's dividing up your input into 2 different sections. It basically lets you flip a single bit anywhere in memory and then returns up the stack and quits. And all you need to do is write a small function that interacts and builds up a payload that packs the number in the right way, and you can flip bits anywhere in memory. And then you kind of need to extend it a bit so that you get rip control and do some other cool stuff. And yeah, now the job is how are we going to use our bit flipping machine to actually get shells, which I think is a really, really cool challenge. So welcome, good to have you around, Parks. I'm not your supervisor, indeed. Yeah. OJ's got... You know what, OJ? I haven't looked at the updated version of that binary yet. I should look at that for you. Sorry about that. I completely spaced on that. OJ's working on some cool binaries for B-sides, so get among it, people. Alright, we've got to paint some shellcode somewhere in memory. and then use our rip control to go to it. We could be tricky. We could like paint the shellcode like just after here and then basically flip this into being some sort of NOP-ish equivalent. But since we've got this rip control thing going on, I'm just going to find a whole slab of zeros somewhere in the program and paint our shellcode there and then ret to it. Because the cool thing is the bit flipping machinery leaves the area of memory as being executable. So that's going to give us a det bypass. Like we can just go and paint our shellcode onto the heap and then return to it, and we should be fine. The challenge is going to be basically how do we take shellcode as an input and produce a series of bit flips as an output to paint it into memory. And that's going to be a cool challenge. So let's give that a go. Let's have a look at the segments and have a look at the data section and see if we can find a bunch of nulls somewhere. So the segments in a program, in a binary, are a whole bunch of different areas. Like the .text segment is the program code. The .plt and the .plt.got are to do with the way that Linux resolves imports from external libraries and keeps track of where stuff is in memory. And then data and BSS, I don't know the difference, but I think, is data used for the heap? And RO data is used for static global variables? Something like that. Like RO data is used for globally defined string constants, whereas data is maybe used for globally defined non-constant strings, and then data and BSS is used for the heap, maybe, or is the heap somewhere else? Yeah, I've got IDA living in Windows because reasons. As far as I know, if you're going to buy IDA, I think you should buy the Windows one. I think it gives you more compatibility with people's published plugins and stuff. I think it might be less buggy as well. I think when I bought IDA, someone said to me, "Hey, make sure you get the Windows one, even if you need to run a VM. It's worth getting Windows." Heap somewhere else. Okay, I was being a complete liar. Thanks, OJ. We should probably just jump into GDB and go hunting for a slab of nulls somewhere, and then hope that produces a reliable exploit, and hope that on different systems, stuff like libraries don't go and jam a whole bunch of non-null stuff into wherever we pick. Because if a library did that, or if some system decided to use memory a different way, we'd be painting shellcode onto an area of memory via bit flips that already had junk in it, so it would corrupt our shellcode. But let's just go ahead with the theory that it should be safe to do as long as we find a bunch of nulls somewhere in memory. Yeah, let's do that. Then again, if we find somewhere inside .text, because text is read-only, right? Then there's no system in the world that should go and munge the read-only version of .text. Yeah, we should be safe. As long as there's space at the end of a page. Let's do that. What's the address of .text? Here-ish. So this is the beginning of text, and we can see we've got a whole bunch of nonsense. Let's go all the way up to F00. It's not null. Pants. E00. D00. Yeah, looks like .text is just full of bits and bobs. There's no area for us on that page, at the end of that page at least. Maybe there is halfway through the page. Okay, yeah. .text finishes at 902 and .fini starts at 904, so it looks like the rest of the page is actually in use by a different segment. Fizzer. What about the page that the PLT's on? It should be a pretty small PLT. Unless it all kind of... Does it all sit on the one page? Yeah, it all does. It's all back to back. Sad face. We should be able to find a whole bunch of nulls somewhere. Maybe in .data. Or .bss. Let's check .bss. Examine 8 hex at that address. And it's already starting to look good. A bunch of nulls there. Let's go at E100, E00. That looks like enough room for shellcode, yeah? Yeah, there should be enough room for shellcode. And it's all null, so I think we'll just paint our shellcode at this address here, and then return to it once we're done painting. Yes, indeedy. If you want to hear us say nonsense throughout the week, not just during a couple streams, then follow us on Twitter, and you can hear all the nonsense we'll be willing to punch out. Are we talking about Binger? Yeah, cool. And here I am getting schooled on memory segmentation. Thanks, thanks guys. Data's for global initialized that are writable. BSS is for global variables that are not initialized, but also writable. And R data is for non-writable. Okay, yeah, cool. Thanks, thanks Mongo. Yeah, big +1, Jim. It's Binger's much more affordable. Do you need nulls? Can't you just calculate the binary XOR of some? Yeah. Yeah, totally could. You're right, Infinite. Yeah, sorry, I derped for a second. What I was more worried about in thinking of that was, you know, yeah, no, you're right. I can, that's going to be a much more fun exercise, actually. Let's do it that way, Infinite. Instead of using our slab of nulls, because that's easy mode, let's do this hard mode. Because I'm hoping there's a way that we could read the ELF and actually kind of get an offset at the address, and using Pwn tools, get the current state of the binary code at a certain location, and then kind of calculate, you know, XOR that with our shellcode, and then paint that series of XORs in. That would be, that's a cool. Let's do it that way. Let's pick somewhere that's not full of nulls, and actually see if we can use Pwn tools to automatically calculate what we should paint where to make it become shellcode. Let's do that. OJ called. Yeah, you're right. I was being lazy. But no, if you just heard what I didn't read this, but I'm willing to not be lazy. Let's do it the hard way. It's only 10 o'clock. Who needs sleep? Hisukun, is it? Yeah, ping me with what I may otherwise know you as, because yeah, if we met at KiwiCon, I'd love to put a mentally put a face to the name. So hit me up and let me know what who I may have met you as. That way, I can tie that, close that loop off. That'd be wicked. I'm sure it was lovely to meet you. I'm sure once I find out who you are, that I'll be able to say that in all honesty. Let's do this the hard way. Let's do it the proper way. Let's pick somewhere in memory that's not... Should we just pick straight after main? Just kind of... Yeah, let's pick straight after main. Like, where's this return at? Actually, where's this jump at? Is this here right after the ret? No, so here's the ret, then here's some other nonsense. Should we blast the stack canary check fail function? I was just thinking, how is that stack canary check passing? But we're not actually messing with RSP tool down here. Yeah, so this canary check is working just fine. Let's start here. Let's start painting our shellcode there, because if we go to that in the hex viewer, then yeah, this is a whole bunch of not null. Let's do that there. And then we're heading off into the strings of the binary. Is that going to cause us problems? Like, what segment is this? 400910. RO data. That should be fine. As long as we're not going ahead and smashing the PLT, we should be okay. Yeah, I think we'll be safe. We may start to see shellcode and stuff be punched out in the banners, but that shouldn't be a problem. There should be a null somewhere that should stop it. Yeah. Yeah, we should be able to destroy all this and not have it matter, right? Well, one way to find out, may not be a totally reliable exploit, but it's going to be a fun little project. Let's go ahead with it, even though it may not be the best thing we should be doing. I'm going to have used basically this here as kind of like picking an address at random to see if we can succeed with a randomly chosen address. So we're going to start painting our shellcode at this address. I'm going to take a quick 2-minute break to fill my water bottle up, and then we will get underway with the shellcode painting. Stick around if you want to see that. If not, I know it's late and I totally understand if you need to head off. But if you want to stick around, now is a good time for a quick 2-minute breather, and we'll commence shortly. Alrighty, let's put shellcode in places where there shouldn't be shellcode. And get shells to pop when shells shouldn't be popping. So, in case you missed it, I've decided basically, and I think Mongo, I saw a tip that in some view or another you'd see the segment name down the bottom. So you see the segment view here, the segment name in this view. Then why did I see strings and stuff? Hang on, let's go highlight this location and go to the hex view. Alright, so you see no segment name down here. This must be the code that I was seeing in the disassembler, but then the strings kind of kick off pretty quickly. RO data. Okay, so here's like the function name. There's the function name, but when you come down here, you can see .ro data. Okay, cool. So we're going to go and do some messing with .ro data, which should be... we're going to mess with some of... I was seeing Emprotect 1 and I was freaking out, but this is just in RO data because it's what's used to do some error printing. We're going to smash this here, EH frame header. Hopefully that's not important. That's if our shellcode shouldn't go that far. We should be fine. Our shellcode may not even go this far. We should be okay. So where's our... Yeah, so I've picked this location, kind of at random, because I know it's something that... Why did I had to go there? It's not at all... Why did it jump around? Stupid thing. Okay, cool. Go back here. I don't know what... I just clicked then, but something weird happened. This is some memory that we've kind of been seeing out of the corner of our eye all night, so it's a good candidate for picking something at random, and we know that execution doesn't go here, because this is the stack canary failure section of the code. We know that execution normally goes down here, so this, if we modify this, won't actually influence the execution flow until such time as we decide to return to it with our rip control. So it's at 400,883 that we're going to be messing with. Undo kappa, indeed Wilkins. Alright, so pointer to... we'll call it pointer to shellcode equals... Can't type with the microphone. I can't type anyway, but especially with the microphone in my face. So the pointer to shellcode is going to be that. We don't need these anymore. These are just the bit... Actually, you know what? Let's keep one of them. But comment it out. We don't need to flip the bits inside the string anymore. Right. So we're going to do some bit flipping at this address to cause it to become shellcode. So let's just go, let's do some logging. pwn.log.info give rip control via jacking the amount added to RSP in mains epilogue. So we do that. Let's go and put this down the bottom here. Let's be hopeful. pwn.log.info enjoy your shell, hopefully. When we go t.interactive, we're going to get a whole bunch of thou art God spewed onto the screen, but that'll be fine. So it's in here that we need to pwn.log.info inducing shellcode at address 0 : is it #08x to give a pointer in Python's string function formatting stuff. .format pointer shellcode. To do. Oops. So if we run that, what do we get? We get all our pretty logging happening. Yep, and that is how you print pointers in format string land in Python. Enjoy your shell. Hopefully we don't have a shell just yet. Cool. So now, I'm thinking we should generate some shellcode. Shellcode equals pwn.assemble pwn.shellcraft.i386.linux.shell. I think that's what we want. Python import pwn. Because we don't need a full-blown, reverse TCP shell. All we need is shell, bin shell to be executed by the victim process, which hopefully will be this here. We then need to assemble it. That should be all we need to do. This here, which looks to be like shellcode to me. If we just go and print the inner part of that, then we get this here. That looks like shellcode to me. So this here is going to be the shellcode that we paint into memory. So, yep, nailed it. So that's the shellcode. Now what we want to do is we basically want to go and get shellcode number of bytes of the original binary. Now we could do that by coming over to IDA, clicking on this, going to the hex view, and copying this here. But that's boring. I want to see if there's a way that we can use pwnTools, because pwnTools actually has a copy of the ELF loaded, actually by means of the tube. So we should be able to, normally you wouldn't do this because you'd want to be able to adjust this exploit here to then point to a remote host, and off she goes. So you wouldn't normally do it this way, but just so we can kind of learn a bit more about the functionality that pwnTools gives us as exploit developers. I want to see if there's a way that based on the tube, which we know to be T, to be, hey, pwnTools, go and get the binary that is on the other end of this tube off disk, which is going to be like basically, open this file, and then parse it as a ELF file. And then go and give me a whole bunch of bytes at this offset of the ELF as it would be mapped in memory, and return it to me. And I want shellcode number, the length of shellcode number of bytes. I reckon there's got to be a way that pwnTools will let us basically slice and dice the ELF in and of itself just based on the tube T, which should give us then something to XOR against shellcode, which then should give us the bits that we need to induce flips in. Do we need to XOR? I think we need to XOR. We need to take the state of memory, XOR it with the shellcode, which should then give us the bits that we need to XOR in memory to make the memory become the shellcode. Someone correct me on my bitwise mathematics if that's not correct. That's the way I'm going to go about it for now. I should probably stop to think if that's actually what I want before I continue. I'm going to check that chat do, and then I'm going to have another think about if that's what I want. But that's the idea. I want to see if pwnTools can basically slice and dice the ELF for us and make decisions about which bits to flip, so we don't have to do it ourselves. You leave for now and you're already lost. Sorry about that. So the one you ignore, we're not ignoring you, despite your name. What we've figured out so far is basically how to interface. I don't know what you've missed in the last hour. Maybe you caught the bit where we learnt how to interface with the bitflip API. And maybe you missed the bit where we figured out how to get rip control by twiddling a single bit inside main. We actually went and we spiked... that's not main, this is main. We went and spiked this bit here, a bit within this value, this OX48. And by targeting and spiking that byte in one of the bits therein, we were able to make sure that at the end of main, RSP didn't have enough added to it to rewind the stack properly. So the stack got partially rewound into an area of the stack that we control due to the fact that string to long ignores trailing garbage. We actually went and put a null byte in there as per Mongo's advice, and then put some garbage, and we're able to influence rip that way. And so by influencing rip, we make sure that we not infinite loop, but we induce a loop within the return here to cause the return to this sub RSP OX48 and cause main to happen again and again. That way we get multiple shots at flipping the bit, and now we're onto the bit where we basically paint shellcode into memory via bit flips. And then finally what we'll do is we'll use our rip control that we got through messing with this byte here to return to that shellcode, and we should get a shell. So that's what you may have missed in the last hour. Yeah, big +1, Pellies. How good's pwnTools? Oh, neat. Thanks, Infinite. Yeah, I've been meaning to look into whether there's a better Python REPL than the one I use, so I will check out PT Python. Thanks very much. Let me bookmark that in my personal browser so I don't forget about it. It's amazing how many bookmarks I end up throwing into my browser based on these streams. I think I learn more than anyone else here. So thanks for that. Okay, yeah, that's what you missed. Hopefully that very quick summary caught you up somewhat. Alright, ELF processing in Pwning. Pwning doco. I was trying to be cheeky. Pwning doc. That's what we want. This looks good. There's so much cool stuff in Pwning. You go digging through the doco and you find so much neat stuff. Like, it can actually give you a dictionary of name, colon, address for all functions in the PLT and in the GOT. Like, that's cool. That's way cool. You can get the libraries. Yeah, you can do cool stuff with Pwning. So this looks good. We could use this function here to translate a virtual address. For example, Mongo. I thought you used Pwning Mongo. I thought you did. Maybe you and I'll talk offline about what you used to use that I know of. But yeah, Pwning is quite neat. It gives you a lot of helpers to make you have to do a lot less work, so you can be lazy. I do suggest to everyone who hasn't done any exploitation before to not start with Pwning. I think it disguises some stuff. First of all, I think it disguises some stuff and does a disservice to you if you start with Pwning. But second of all, I'm angry because I used to do stuff the hard way and you should have to as well, god damn it. But I do think people who are new to exploitation should start without Pwning, should do a couple of things like stack buffer overflows and stuff without it, because otherwise it can hide some of the workings of certain things. I think you should know how to do socket handling within Python before you graduate to just doing pwn.remote and giving it a port and address. So I think for people who are new to exploitation, they should start without Pwning. But once you've got a couple of exploits under your belt, pick up Pwning. It makes life so much nicer. And it gives you just stuff like this. Like, we could use this function here to translate a virtual address such as this here, pointer shellcode, into a absolute file address, like an offset into the file, and we could just do, open the file, seek to that location, and then read some bytes. But I'm holding out because I reckon there's going to be a function that does exactly what we want to do for us. But it's still cool to know that you can do this should you need it. There's just so much neat stuff in Pwning. Although I'm hitting the end of the page, so maybe there is no... maybe I was wrong. Maybe there is no... Maybe there is no give me the bytes at this virtual address. Maybe we do need to use this and then actually open the file and seek. Perhaps. Well, not open the file and seek. We can use... I did see that there was... hang on. Read. Perfect. I did see before that there was something else we could have... Get data. Yeah, you get the raw data from the ELF file, but we can just use read. Read data from the specified virtual address. You give it an address, the virtual address to read, and then the count, the number of bytes to read. That's exactly what we need. The elf.read. Now what we want to do is we want to get the elf file out of the tube. So we want to be able to refer to the tube and get the elf file. So let's keep this in mind, and we'll go pwnlib.tubes. Where's my tubes doco at? Here we go, tubes. We should be able to get the elf file that relates to a tube. Oop, maybe not. Let's go pwn.process. Maybe you can't refer to a tube and get an elf. Maybe we've actually got to do some hard work. Alright, let's go on that assumption. Let's just get the elf ourselves. Let's quickly just go and lift this string here into bin name equals that. Let's change that to refer to bin name. That way we can get the elf based on bin name. Let's go e for elf equals, because I'm super lazy yet totally imaginative like that. E equals, how do we actually load an elf? We don't want tubes, we want elf. pwnlib.elf.load. That's good. No, we don't want that. pwn.elf.elf. We give it a path. Oh, hang on, that's not a... Is it a variable? Is it an argument? Yeah, I think it's an argument. Ah, well, that's not what I thought it was before. Let's go e equals pwn.elf bin name. Let's just go print e. And we should actually have an elf object. Huh. Actually prints out, actually like pretty prints it. With architecture and basically the check sec. Way to go, Pwn Tools. Okay, so it looks like we've got an elf. So e equals pwn.elf bin name. Now we want to go and do a read on it to actually get the bytes at the virtual address of where we're going to put our shellcode. Let's go read bracket. So it takes two arguments, the address and the count, and returns a string of bytes. Let's go elf shellcode orig equals e.read. We want to read at the pointer to shellcode, and we want number of shellcode bytes. So we go len shellcode. And then let's go print. Let's go print elf shellcode orig.encode hex. Okay, so this here is what Pwn Tools is telling us is at the virtual address pointed to shellcode. So now we should be able to compare E888FD to what's in IDA. E888FD. E888FD. Perfect. Looks to me as though E888FD FFFF0F1F FFFF0F1F. Yeah, so Pwn Tools has gone and carved out these bytes for us just using this here, and that's a really nice way to basically be able to do it in the face of a binary that may change over time. Pwn Tools will automatically go and re-carve out those bytes so you're not copy pasting them from IDA. That's super neat. I'm a fan of that. Now we need to basically decide which bit flips to induce where within this string, or this byte string at that address, to cause it to become this here. So to do that, we're just going to basically get this, XOR it with shellcode, and that should basically give us the bits that differ. Is that right? Yeah. Because if our shellcode is 0 and their remote host is 0, or the process contains 0, we should get a 0, which means don't flip. Whereas if they're 1 and we're 0, or we're 0 and they're 1, then the XOR will give us 1, which means go ahead and flip at it. If we're both 1, we don't want to flip, we should get a 0. Yep, so we just want to XOR elf shellcode orig against shellcode, which should give us the byte string that we need to basically induce XORs as per to achieve shellcode at that location. And then we should be able to just basically in GDB break and then do examine a whole bunch of instructions at that address, and we should see our shellcode. So now we need to basically map the XOR function against 2 different byte strings, which is going to be awesome. Well, they're already, yeah. So for example, Python. Let's go like a whole bunch of A's. Let's go 4 A's. If we were to map XOR against 2 lots of that, then we should be getting a whole bunch of null bytes back. So how do we map XOR against 2 different byte strings? Can we go like A XOR A? Let's go ORD A XOR ORD A. We get back 0, yep, then we go the character 0, and we should get the null byte. Yeah. Whereas if we XOR A and B, then we get OX3. Really? Oh, yeah, that kind of makes sense. Let's go man ASCII. Actually, that's not. Because character A is OX41. Nope, sorry, hex ORD A is OX41. So the binary of OX41 is that. The binary of OX42 is that. So if we'd XOR these 2, then we'd get binary 1, 1, which is 3. Yep. So all we need to do is basically map the XORing of the 2 different ORD values of each character across the whole lot of, yeah. So if we do, is it zip? We can zip AAAA and BBBB, then yeah, we can pair the characters up. If we go and zip AAAA across BCDE, then yeah, it maps up the A with the B, the A with the C, the A with the D, and the A with the E. And then we should be able to, from that, is it map? Map the function against that list? How do you map functions? I'm kind of new to this way of thinking about stuff. I'm sure OJ's going to be able to rattle it off in chat, but I'm going to see if I can get this without checking in with what... OJ, go and rattle the solution off in chat and let's see how close I get. If OJ's still around, I know it's getting a bit late-ish. So how are we going to map XOR against that list of pairs? We need like a anonymous function or a lambda function or something. I'm gonna quickly Google this because I'm not gonna get it from memory. Python lambda function. That looks good. Lambda, oops, didn't see the chat there. Lambda x is the character of the ORD of x0 XOR the ORD of x1 bracket. Yeah, that's what I want. OJ, how'd I go? Is that how I should be basically XORing two byte strings against, and then just do empty string.join? There we go. OJ, how's that look for a byte-wise string, byte string XOR function? Did I win? Map lambda xy. So you don't have to actually, like, you can actually have a lambda that. Okay. Zip. Oh, so you zip map. Oh, okay, so you do the ORD there. I pulled the ORD into the lambda. Yeah, thanks OJ. I know that the lengths do match because I've actually gone and pulled out X shellcode, elf shellcode orig to be the length of shellcode, so I know their lengths match. But yeah, I know that you have to itertool cycle one of them if it's, like, for example, a key. Yeah, cool. Cheers. All right, cool. I did a thing. So I don't want to print that anymore. Now we want to do. This is basically going to give us a map of bits to. I'm probably digging myself in a big hole here, but this is going to give us back a map of which bits in memory to XOR. I think I'm digging a really, really deep hole here, but I'm going to keep on digging. It's all I know how to do. So I'm going to call this the XOR map equals empty string.join. I'm going to map. Do I need a bracket there, or do I just? Yeah, I need a bracket. Map lambda. Map lambda x to be the character. ORD x0 XOR. XOR, damn it. ORD x1. So that's my lambda done. Against zip of shellcode against elf shellcode orig. I'm probably giving the actual programmers in the room here an absolute heart attack with this, but print XOR map.encode. This is not going to speak to me at all, but it's at least going to, as long as it's not all Fs or all zeros, I'm going to be happy. What's your problem? Print XOR map.encode hex. I'm missing a bracket? Yeah, I'm missing a bracket. Alright, that looks like some sort of XOR map. Yeah, let's go with that. At least it's not all zeros or all Fs. So this here is basically the map of which bits to XOR. What are we going to do with this now? How are we going to work through this and do the XOR in the right place to achieve shellcode in memory? And yes, I'm making this. I'm doing this in hard mode because I want to learn some stuff. It would have been so much easier to just blast out the shellcode into an area of memory that was already 0, but now we've got to actually obey. It actually wouldn't be that much harder, that much easier to do it that way, because we'd still have to basically do the same thing we're up to now. The hard work should be out of the way. So like we can loop through this byte-wise to get each byte one at a time, and then we can either maintain a counter or do some other trickery to know at what place in memory we should be up to. And then we just need to basically explode each byte into bits and then do the needful for each lit up bit. That's one way of doing it. Is there an easier way of doing this? Oh, list comprehension instead of a map. Yeah. Character or that for XY in zip. Yeah, that's a much nicer way of doing list comprehension. Thanks, Infinite. That's an alternative that looks much nicer than my ugly map solution. Cheers. Map tends to be faster. Yes. Did a thing. But yeah, I agree. Wilkins' list comprehension is beautiful. Yeah, now we get into the fight in chat as to which is more optimized. Love it. We could loop through, you know, for each character do, and then we could end it with 1 to find out if the lowest bit is set. If it is, then go and do a bit flip at bit 0 or bit 1, I tend to call it, in the remote process, and then just shift it down by 1 and loop on that. So for each byte we could loop through the bits and then just keep shifting it down and ending with 1 to find out if there's a bit lit up there. Is there an easier way of doing it than that? That feels super janky. That feels super nasty. Is there a nicer way to actually basically use this XOR map to do the needful on the process? Can't think of one. Maybe I'll just go ahead and do that to prove the concept, and then maybe if we're still feeling like it, we can optimize what I've done into something that's not disgusting. Let's do that. Let's do the it's temporary for now, but then it's going to make it into production strategy. So for C in XOR map, do so we should be able to go print c.encode hex to make sure this loop works, because I've got trust issues right now. Yeah, so we can kind of loop through each byte one by one. Cool. Do we need to maintain a counter, or can Python do that as part of a for loop? Python for list maintain counter. Does Python give it for free? Maintain count in Python list comprehension? Enumerate. That rings a bell. Yeah. That looks good. So if we just go and wrap XOR map and enumerate, we should get the counter for free. We for C enumerate that, print, let's go print C0 and print C1. I'm sure there's probably a better way of doing this. Print dash dash dash. Yeah, we get like a counter for free as well as the actual byte. Is there a better way than actually exploding that list? Like, yeah, there is. For index and the character, print I and print c.encode. No, print index. Yeah, that's what we want. Alrighty, so we've got a counter for free using enumerate. Hooray. Alrighty, so what we want to do is then, once we've got that byte, for I in range, because I'm stupid and didn't zero index those bits, I'm going to have to do 1, 9, because range 19 is going to give us the numbers 1 through 8, which is how I tend to reference bits because I'm stupid and didn't allow the zero indexing as nature intended to bubble through. My API was written with one indexing in mind because I'm not smart. So for I in the range 1 to 9, we want to do... actually, you know what? No, we can afford to do 8 because we're going to do some shifting here. Yeah, so for I in range 8, which is going to give us the numbers 0 through 7, do if character, if the ord of character, so we need to cast it to an actual number, shifted to the right, for shift, I shouldn't use I there, so we want to shift it down by shift, if ord C shifted right by shift and 1 is set, then we want to flip bit at pointer shellcode plus index, which is going to be the index at which we are in the XOR map, and we want to shift the I should have zero indexed my API to the bit flipping API. We want to flip the shift plus 1th bit. I think that's what we want to do. We need to give a rip as well, and rip is going to be pointed to mainish, so we at least loop back on main. So if we let this loop run, it's going to enumerate XOR map and return a list of tuples as per this kind of thing, ABCD. Enumerating ABCD, we need to cast it to a list so we can actually print it. It's going to give us, yeah, an index and then a character, an index and a character, an index and a character, index and a character as tuples within, not within a list, but within an enumerate object. So we're going to, for index and C in the enumerator, which dishes out tuples, we're going to do for shift in range 8, which is going to give us 0 through 7, so we can test all 8 bits, we're going to shift ord C down by shift. So like in the first iteration, we're going to shift it down by 0, which is going to do nothing. Then we're going to AND it with 1. And if that results in a bit shining through our mask, then it means that the shift plus 1 bit, because I didn't zero index stuff like I should have, needs to be bit flipped. So then we're going to do a flip bit at pointer to shellcode plus index, because we're using index to track how far through the XOR map we've reached, and cause a loop back to the top of main-ish. I'm gonna just clean up shop here, get rid of that. So we're going to do that. We're going to flip the bit, and then we're going to enjoy your shell, and we're going to go to interactive, and we should then be sitting at the API to flip bit. But we should be able to then break in GDB and see if our shellcode has made it into memory at the address pointed to shellcode. Let's see how we go. Let's watch the Python syntax errors spew forth. Ah, we didn't get syntax errors, we just got a bunch of banners. That's good. Makes me happy. So if we break GDB and examine 16 instructions at this address, fingers crossed, we'll get our shellcode. This is looking like the shellcode that I know and love from PwnTools. Let's go and just go Python, import pwn, print pwn.shellcraft.i386.linux.shell. Push that, XOR EDX, EDX. Yep, this is our shellcode. Push RDX. It's not 64-bit. That should be i386-64 maybe, because we need 64-bit shellcode. Nope. Maybe it's x64. Nope. Maybe it's x64. Nope. All right, I need 64-bit shellcode. I don't want 32-bit shellcode. Otherwise, it looks like the theory is sound. That yeah, we've actually got. Let's go and print some more instructions. Oop. Let's examine 32 instructions. Yeah, here's our in80. Yeah, so that shellcode looks fine. The theory is sound. We have painted shellcode into memory. It's just not the shellcode we want. Let's go Pwn tools. Let's go shellcraft. How do I get 64-bit shellcode? Shellcraft. Shellcraft.amd64. I was close. Yeah. 64-bit shellcode. Yeah, thanks, Peleus. I know you got my back. All right. So let's not do shellcode equals that. Let's go shellcode AMD64. That's the neat thing about doing stuff like this here. Means that when you go and when you've caused an error earlier on, like having the wrong flavor of shellcode, you've got to change it in one place, and then everything cascades through. Like your length shellcode automatically adjusts. Everything makes you happy. So we run the exploit. But bad things. What have I done? Is the assembling failing? I bet it's the assembling. Python import pwn. Nope. pwn.shellcraft.amd64.linux.shell. We print it. That looks fine. But if we go and try and assemble it, I bet we need to do something special for AMD64. Pwn.assemble. Yep. We get sadness. How do you assemble stuff to be 64-bit? If we, yeah, we should probably actually set the context of pwn. It's probably what we need to do. Yeah, architecture is selected using pwn.context. So like we did up here for setting the terminal to be tmux, we need to set the context for the architecture to be 64-bit. So we need to look up how to do that. What have I missed? OJ, good to have you around, dude. I'll catch you on the tubes, hey? Thanks for your help tonight. We've actually benchmarked our Python. That's so good. I love you, chat. So list comprehension is quicker and map is slower. Thanks so much, Wilkins. That's good to know. Right on. We've almost got this. We need to figure out how to set the pwn context to be 64-bit. Arch equals. I'm guessing arch equals AMD 64. Arch equals AMD 64. As a string, I'm guessing. Yep, as a string. Alrighty. Oops, I fail at saving files. There we go. Let's run the exploit. Hopefully we get 64-bit shellcode where we want shellcode. Looking good. Yep, that looks like we know. That looks like the shellcode we know that Pwn Tools produces. And we got a syscall. Alrighty. We should be almost home and hosed. All we need to do now is, well, the smart thing to do would be making sure that this loop here ensures that for the very last thing that it needs to do a bit flip of, it causes the rip to actually be pointer shellcode, not pointer mainish. You know what? We can just go and flip the bit. I knew it was going to be handy. Let's just go and flip the bit in that string that was being printed. right here, we were flipping this a bit in this capital H. Instead of pointed to mainish in the rip argument to this flip bit, let's go and make the rip argument be pointed to shellcode. And with just one extra gratuitous bit flip, we should be able to cause execution to flow onwards to our shellcode that we have painted into memory. So crossing our fingers, running the exploit, we get process, it's executing a new program, bin dash, and we can go ID, and we've got a shell. Very cool. So that is how you solve the butterfly pwnable, and I think it's a really cute challenge. It's how you use a bitflip-as-a-service process to get shells. Obviously, to exploit it in the way we've exploited it, we needed to have a copy of the binary, so we could do things like determine the address of where that add ESP amount was that we wanted to spike. And we also needed a copy of the binary to know what was originally at the location pointed to shellcode, to then create this XOR map that would then give us an indication of which bits we had to flip to induce shellcode at a given address. But yeah, given a copy of the binary, we can get shells out of a bitflip-as-a-service process. So thanks everyone for sticking around and seeing that one through. I had a lot of fun. Hopefully you did too. I learnt a lot of things. I learnt how to use IDA even better this time around. And I picked up that I should look into OJ's reading list, and that I should use, was it PTY Python as my Python REPL. Oh yeah, right on. It's actually a GitHub repo. It's a better Python REPL. I will 100% look into that. That looks really cool. Yeah. That looks well cool. I will check that out. Whoever it was who posted that, thank you very much. I appreciate that. Thanks for sticking around. I hope you enjoyed it. I will catch you this Wednesday, I think. I think I'm free this. I think I'm streaming this Wednesday. I don't know what I'm going to be doing, but we'll sort something out. I'm really looking forward to. I've had, as a lot of you know, I've had some bugs in the pipeline with an open source project for a while now. They are dragging their feet quite a bit on a fix, and I can't wait to discuss. I'm actually hoping that if they patch the issue on a Wednesday or a Sunday, or if I can kind of convince them to hold out a couple of days so that their patch falls on one of those days, or if I'm in the mood for doing an impromptu stream, I'd love to do like YOLO disclosure, stream disclosure, and actually push out the advisory and push out a tweet and push out an email to OSSEC or however I decide to publish my advisory on stream, and then we can go through the bugs on stream and get shells out of some freshly patched software. So that'll hopefully be coming up in the next few weeks. I'm really looking forward to it. I hope you'll be there for that one. But Wednesday, I don't know if I don't think they're gonna fix it in time for Wednesday. I don't know what their plans are. They punched out some patches and sent them to say, hey, does this fix like the 5 bugs you found? They submitted a patch for 3 out of 5, and some of them were bypassed. So I sent them back and said, nope, you'll need to try again because here's some new POCs that bypass those fixes. And the project's gone a little bit quiet on me, so fingers crossed we'll get some patches soon and we can do some disclosures and some hacking of some end-day bugs on stream. That's it from me. Thanks very much for your company tonight. I very much appreciate it when people show up to watch me do dumb stuff. So thank you very much for hanging around, and I'll catch you on Wednesday. Take care.